Lab 2, in which we analyze the motion of a falling object and observe the forces acting upon it according to Newton's second law. The purpose of this lab is to observe the effects of both acceleration due to gravity and drag on, in this case a crumpled piece of paper, as it falls to the ground. When I recorded the motion of the crumpled piece of paper as it fell, I found as I incorporated drag force that the model overpredicted the free fall of the object. After incorporating drag, there was still some error, but less than without drag. Here we see Newton's second law as it relates to the velocity and position of the object over the given time interval. The weight force and the drag force both factor into the net force of the object. Newton's second law here states that the final velocity is equal to the initial velocity plus the F net over m multiplied by the change in time. The final momentum is equal to the initial momentum plus v average multiplied by the change in time. Also, the weight force is equal to the mass, negative mass times gravity times j hat, which tells us the direction of the weight force, and the drag force, which is equal to negative b, that's the drag constant, and the average velocity squared. In this case, this is not the viscous drag force, but the turbulent drag force acting upon the object. Here's my tracker fire where I analyze the motion of the crumpled piece of paper over the 0.6 second interval. My crumpled piece of paper falls along the negative y-axis, and my length scale was my friend Audrey's height, which is 1.88 meters, and the motion is tracked, as you can see, in this negative parabolic shape, which shows a negative acceleration is occurring. That was the experimental data. Now for some excerpts of the code which I used to model the motion of the crumpled paper over the 0.6 second interval. I estimated the paper's mass to be 0.0045 kilograms. The initial position of the paper is 0, and the initial velocity is 1 in the negative y direction. In this block of code, I set 9.8 as 9.8 as g, 9.8 meters per second squared, and the direction of motion to the positive y direction. The proportionality constant to 0.00116 after some experimentation. And here is the main chunk of code that models the motion. This loop iterates through the entire period of motion, which is 0.6 seconds. Here we see the two forces that factor into the net force. First, we have the weight force, which is mass times Earth's acceleration multiplied by the upward direction vector. And this force is negative because it pulls the object down. The drag force is the proportionality constant multiplied by the magnitude of the velocity multiplied by the direction of velocity, and this value ends up being positive because it pushes upward on the object, modeling air resistance. The net force is both of these forces added together. Each time this loop iterates, it updates the velocity, position, and time using Newton's second law. To see the difference drag force would make, I ran it once without drag force and once with drag force. In the graph where drag force is excluded, the data shows that what free fall would look like if the net force were only equal to the acceleration due to gravity. And here you can see there's a great deal of error between the experimental and theoretical model, as the theoretical model greatly overpredicts the experimental data. Here in the position versus time for my free-falling object with drag, I selected the value of the proportionality constant with the interest of having the theoretical data and in the same position as the experimental data. That's why there's less error in this model, but there is still quite a bit of error. Now let's take a look at our discussion questions. Neither of these models suggest the terminal velocity. That's probably because the distance is too short to have air resistance strong enough to produce the terminal velocity. If the object were thrown down, terminal velocity would remain the same. it would begin its motion with the higher initial velocity due to a force that is quickly removed, so the final net force would still only have the weight and drag force present. To prove this, I entered a non-zero downward initial velocity into my computational model, and the prediction showed a near constant velocity developing at the end of the motion. Thank you for watching. This was Lab 2.